the last chapter, the last chapter, the last chapter. Chapter 20. Final project, building a multi-threaded web server. Okay. It's been a long journey, but we've reached the end of the book. In this chapter, we build one more project together to demonstrate some of the concepts we covered in the final chapters, as well as recap some earlier lessons. For our final project, we'll make a web server that says hello and looks like figure 20-1 in a web browser. So yeah, localhost 8080, hello, hi from Rust. Here's the plan to build the web server. Learn a bit about TCP and HTTP. Listen to TCP connections on a socket. Parse a small number of HTTP requests. Create a proper HTTP response. Improve the throughput of our server with a thread pool. But before we get started, we should mention one detail. The method we'll use won't be the best way to build a web server with Rust. A number of production-ready crates are available on crates.io that provide more complete web server and thread pool implementations than we'll build. However, our intention in this chapter is to help you learn, not to take the easy route. Because Rust is a systems programming language, we can choose the level of abstraction we want to work with and go to a lower level than it is possible or practical in other languages. We'll write the basic HTTP server and thread pool manually, so you can learn the general ideas and techniques behind the crates you might use in the future. Alright, so in this chapter, we're just building a web server that does something stupidly simple, but we're going to take the hard route. We're going to go down to the lower levels and write the basic HTTP server ourselves, write the thread pool ourselves, just so we can learn those concepts. And it should be noted, this is not a realistic way of writing it. There are crates to do this for you, which they link to crates.io, but you can just search for them on crates. It's like a category, I believe. Anyway, moving onward. Building a single-threaded web server. We'll start by getting a single-threaded web server working. Before we begin, let's look at a quick overview of the protocols involved in building web servers. The details of these protocols are beyond the scope of this book, but a brief overview will give you the information you need. The two main protocols involved in web servers are the Hypertext Transfer Protocol, HTTP, and the Transmission Control Protocol, TCP. Both protocols are request-response protocols, meaning a client initiates requests and a server listens to the requests and provides a response to the client. The contents of these requests and responses are defined by the protocols. So yeah, just going over HTTP and TCP, which I always forget the full name for them. Hypertext Transfer Protocol, HTTP. But the Transmission Control Protocol, TCP, I always call it TCP. Never really knew it was transmission, but that makes sense. TCP is the lower level protocol that describes the details of how information gets from one server to another, but doesn't specify what that information is. HTTP builds on top of TCP by defining the contents of the requests and responses. It's technically possible to use HTTP with other protocols, but in the vast majority of cases, HTTP sends its data over TCP. We'll work through the raw bytes of TCP and HTTP requests and responses. Yeah, we typically use TCP connections for most things. There's UDP protocol, and I believe TCP is going to get replaced soon by like UDP over HTTPS, something along those lines. Google. But that's a story for another day. Listening to the TCP connection. Our server needs to listen to a TCP connection. So that's the first part we'll work on. The standard library offers a standard net module that lets us do this. Let's make a new project in the usual fashion. I don't think it has to be a new project per se. I'll just use this old one. But yeah. They did a cargo new hello. This is going to be their hello project. Now enter the code in listing 20-1 in source/main to start. This code will listen at the address 127.0.0.1 7878 for incoming TCP streams. When it gets an incoming stream, it will print connection established. Okay, so localhost at port 7878, and we're putting this stuff in. Copy, well, let's read through it first before we copy and paste. TCP listener, so that's pretty straightforward. And then we're binding the listener to this address and this port. Makes sense. Unwrap in case there's an error. Then we have 4 streams in the listener incoming. So I see this is the synchronous part. Stream comes in, we do this, we print, and then we listen for another stream. Like we drop the connection seemingly. Do we drop the connection? I don't know, we can test this out. Control copy. We have it there. I should probably create a new project just because of this thing. Alright, copying it again. Or pasting it again. Cargo run. And it looks like it's running. So then we can go to this address. Connection was reset. That didn't seem like it worked. HTTP? Is it? Yeah. Go ahead. No, that didn't seem like it worked at all. Connection established. Oh. Okay. It looks like it's working here. Connections are established. And this is trying over and over and over again. Connection seems to get reset because we're dropping it. I see. Yeah, that's annoying, but that was close to a hello world. Close. Let's turn this server off. Using TCP listener, we can listen for TCP connection at the address home localhost 7878 in the address. The section before the colon is the IP address representing your computer. This is the same on every computer and doesn't represent the author's computer specifically. And 7878 is the port. We've chosen this port for 2 reasons. HTTP is normally accepted on this port, and 7878 is Rust type on a telephone. Huh. I did not know Rust typed on a telephone is 7878, but I guess, okay, that's why they chose the port. That's kind of quirky. The bind function in the scenario works like the new function in that it will return a new TCP listener instance. The reason the function is called bind is that in networking, connecting to a port to listen to is known as binding to a port. Yeah, that's very true. You bind to ports. The bind function returns a result TE, which indicates that binding might fail. For example, connecting to port 80 requires administrator privileges. Non-administrators can listen on only ports higher than 1024. So if we try to connect to port 80 without being an administrator, binding wouldn't work. As another example, binding wouldn't work if we ran 2 instances of our program and so had 2 programs listening to the same port. Because we're writing a basic server just for learning purposes, we won't worry about handling these kinds of errors. Instead, we use unwrap to stop the program if errors happen. So they're talking about 2 things, right? One about basic operating system stuff, where if you try to bind to a port under a certain number, you have to have privileges. Those are the root ports. Those have a meaning and a purpose. Everything above that is meh. And then the second one, that we're mentioning is if you try to bind a server to a port that is already in use, as in somebody else is already bounded to it, then yeah, you get an error, and typically you just sort of increment up until you find an open port. The incoming method on TCP listener returns an iterator that gives us a sequence of streams, more specifically, streams of type TCP stream. A single stream represents an open connection between the client and the server. A connection is the name for the full request and response process in which a client connects to the server. The server generates a response, and the server closes the connection. As such, TCP stream will read from itself to see what the client sent, and then allow us to write our response to the stream. Overall, this for loop will process each connection in turn and produces a series of streams for us to handle. Yeah, they're just going over this part. We have an iterator that produces the streams that connect that, and these streams hold on to the request response like tuple thingy. It's probably not a tuple. It may be a tuple. I don't know. I haven't looked at it yet. But yeah, they're just passing that along, and then we act on it. Well, we can act on it right now. We're just printing something and dropping the connection. For now, our handling of the streams consists of calling unwrap to terminate our program if the stream has any errors. If there aren't any errors, the program prints a message. We'll add more functionality for the success case in the next listing. The reason we might receive errors from the incoming method when a client connects to the server is that we're not actually iterating over connections. Instead, we're iterating over connection attempts. That makes sense. This connection may not be successful for a number of reasons, many of them operating system specific. For example, many operating systems have a limited number of simultaneous open connections they can support. New connection attempts beyond that number will produce an error until some of the open connections are closed. So here they're clarifying that the stream thing that we're going over, this is going over all of the connection attempts. So not necessarily just the successful connections. And there are plenty of reasons, operating system specific and even outside of that, why a connection may fail. But those, even the failed connections are going to be in here, and thus we have to have unwrap. Let's try running this code. Invoke cargo run in the terminal and then load. Oh, we did this portion, but the website, localhost 7878 in the web browser. The browser should show an error message like connection reset because the server isn't currently sending back any data. But when you look at your terminal, you should see several messages that were printed when the browser connected to the server. And we did see that. Thank you for mentioning that. That was kind of annoying to see, but yes, we did. Sometimes you will see multiple messages printed for one browser request. The reason might be that the browser is making a request for the page as well as a request for the other resources, like the favicon icon that appears in the browser tab, the icon that happens up here. It could also be that the browser is trying to connect to the server multiple times because the server isn't responding with any data. When stream goes out of scope and is dropped at the end of the loop, the connection is closed as part of the drop implementation. Browsers sometimes deal with closed connections by retrying because the problem might be temporary. The important factor is that we've successfully gotten a handle to a TCP connection. Yeah, I suspect that my browser is doing this. It's just retrying over and over again because it might be temporary. That's why I had to close it. Remember to stop the process by pressing Ctrl+C when you're done running a particular version of the code. Then restart cargo run after you've made each set of code changes to make sure you're running the newest code. Okay. Reading the request. Let's implement the functionality to read the request from the browser. To separate the concerns of first getting a connection and then taking some action with the connection, we'll start a new function for processing connections. In this new handle connection function, we'll read data from the TCP stream and print it so we can see the data being sent from the browser. Change the code to look like listing 20-2. Here we import the prelude, so probably get some extra traits and whatnot. We're explicitly importing the stream because we declare it here as a type for handle connections. This is the same, still binding, localhost 7878. Still doing the for loop where we have the incoming connection attempts. Still unwrap it. What changed is we now pass that stream into handle connections, which the stream is mutable. We create a buffer, mutable buffer, and then it looks like we write the first 512 bytes to that buffer, of the stream to that buffer. And we use this string method to print that out to screen. Okay. My editor, this is the last thing I did, so it's still here. And then we just want to run this. Localhost 7878. Still get the same message because we're not sending anything back to the client, I guess, because the web browser will be the client. Go to the terminal, we see we're getting the same messages over and over and over again of just the header information. So like host, user agent, accepted language, accepted encoding, things like that. But let's turn that off. Get back to it. So yeah, in summary, we just printed out the headers. We read the first 512 bytes and then printed that out. We bring standard IO prelude into scope to get access to certain traits that let us read and write to the stream. In the for loop in the main function, instead of printing a message that says we made a connection, we now call the handle connection function and pass a stream to it. In the handle connection function, we've made the stream parameter mutable. The reason is that the TCP stream instance keeps track of what data it returns to us internally. It might read more data than we ask for and save that data for the next time we ask for it. It therefore needs to be mutable because its internal state might change. Usually we think of reading as not needing mutation, but in this case we need the mute keyword. So the first part was just pretty self-explanatory, just importing the prelude so we have access to some traits that allow us to read and write to the stream, right? This part, they're explaining why the stream is mutable, because typically when we read for something, it doesn't have to be mutable. It shouldn't be mutable. However, this is stating that internally it has to be mutable because the state might change, and that's outside of us. It's just a thing to know. Streams are mutable. Next, we need to actually read from the stream. We do this in 2 steps. First, we declare a buffer on the stack to hold the data that is read in. We've made the buffer 512 bytes in size, which is big enough to hold the data of a basic request and sufficient for our purposes in this chapter. If we wanted to handle requests of an arbitrary size, buffer management would need to be more complicated. We'll keep it simple for now. We pass the buffer to stream.read, which will read bytes from the TCP stream and put them into the buffer. So they're going over this portion, right? TCP stream.read, and they pass in the mutable buffer which we created. And we're just writing the stuff from the stream to the buffer. And what they noted also is that this buffer size, it is contrived for this example because we know it's big enough for this example, but for an arbitrary TCP connection, you're going to need some buffer management to make sure your buffer is big enough and possibly not too big. But you can probably get that information from the stream. Streams typically tell you how large the stream is. Second, we convert the bytes in the buffer to a string and print that string. the string from UTF-8 lossy function takes a slice of U8 and produces a string from it. The lossy part of the name indicates that the behavior of this function, when it sees an invalid UTF-8 sequence, it will replace the invalid sequence with the question mark thingy. The U plus blah blah blah, blah replacement character. They're just noting what the name of what this character is. And I didn't really realize that was the standard replacement, but okay, it is the standard replacement. I've seen it plenty of places, I just didn't know. You might see replacement characters for characters in the buffer that aren't filled by request data. Oh, okay, so there's two things to note here for the second part. One, we have to use, well, we don't have to, there's another method we can probably use that isn't lossy, but for safety reasons, we should probably use the string from UTF-8 lossy function to convert the stuff in the buffer to a string, because we know that the stream is going to be UTF-8, which is under the hood just U8, right? However, if anything doesn't adhere to UTF-8 or is invalid, then we're going to get this feed replacement character. Also, if your buffer happens to be too big and you're trying to read things that isn't really there, it seems as though you will also get this replacement character. So that's good to know. Let's try this code. Start the program and make a request in a web browser again. Note that this will still get an error in the browser, but our program's output in the terminal will look similar to this. Which we did see this, however, our request was so large that we didn't get to this part. I think they just ran out of, like, their buffer is larger than the request itself, where for me it isn't. Depending on your browser, you might still get different output. Now that we're printing the request data, we can see why we get multiple connections from one browser request by looking at the path after request.get. If the repeated connections are all requesting /, we know the browser is trying to fetch / repeatedly because it's not getting a response from our program. Let's break down this request data to understand what the browser is asking of our program. So what did they have here? They have the get / and what did I have? It's still here. We can look at it. Request, they're getting the /, getting the /. So yeah, just requesting the page over and over again. Then they have the host, the user agent of the browser, accepted, yada yada. Let's see what they have to say. A closer look at an HTTP request. HTTP is a text-based protocol, and a request takes this form: method, the request UI, HTTP version, CRLF, which I'm not sure what that stands for, headers, message body. The first line is the request line that holds information about what the client is requesting. The first part of the request indicates the method being used, such as get or post, which describes how the client is making this request. Our client used a get request. The next part of the request line is /, which indicates the uniform resource identifier, the URI, the client is requesting. A URI is almost but not quite the same as a uniform resource locator. The difference between URIs and URLs isn't important for our purposes in this chapter, but the HTTP spec uses the term URI, so we can just mentally substitute URL for URI here. The last part is the HTTP version the client uses, and then the request line ends in a CRLF sequence. CRLF, okay, that stands for carriage return and line feed, which are terms from the typewriting days. So just a new line feed. Understood. The CRLF sequence can also be written as return line, like /r/n, where R is the carriage return and N is the line feed. The CRLF sequence separates the request line from the rest of the request data. Note that when the CRLF is printed, we see a new line start rather than r/n, which is basic formatting and programming. That makes sense. Looking at the request line data we received from running our program so far, we see that get is the method, slash is the URI, and HTTP/1.1 is the version. I didn't actually verify the version. Let's check that out. Yes, it is the version. Cool. After the request line, the remaining lines start from host onward or headers. Get request has nobody. Try to make a request from a different browser or ask for a different address, such as the same address, localhost 7878/test, and see how the request changes. Now that we know what the browser is asking for, let's send back some data. So let's do this first. And in theory, since we're binding to that port, this should just go back to our server and it's just going to request /test. But we can verify. Verify. Localhost 7878 / call it hello. And we get a /hello. Yeah. Nothing too special about that. So now we're going to write a response back. Writing a response. Now we'll implement sending data in response to a client request. Responses have the following format: the HTTP version, status, region phrase, new line, headers, new line, message body. Okay. The first line is a status line that contains the HTTP version used in the response, a numeric status code that summarizes the result of the request, and a reason phrase that provides a text description of the status code. After the CRLF sequence and any headers, another CRLF sequence, and the body of the response. Here's an example response that uses HTTP version 1.1, has a status code of 200 and an OK phrase. No headers and no body. So following the format, we have the HTTP version, we have the status code, we have the region phrase, we have the new lines, 0 headers, new lines, no body. Okay? The status code 200 is the standard success response. The text is a tiny successful HTTP response. Let's write this to the stream as our response to a successful request. From the handle connection function, remove the print line that was printing the request data and replace it with the code in listing 20-3. So what are we replacing? We kept that, and now we're writing the response. And now we're writing the response to response is bytes. I see. Writing it directly to the stream, and then we're flushing the stream. Okay. Just this part. And now we should at least, well, we're not going to get anything, but it should be okay. 7878. Blank page, because we didn't send back anything. Well, we sent back something, but we sent back any content to be displayed. And go here. We should be able to see. Oh, we didn't print out the connection. We're just holding on to it. So one thing I was curious about is, can we do multiple connections? And it looks like it. Okay. Good to know. All right, let's stop this. Continue onward. The first new line defines the response variable that holds the success message's data. Then we call asBytes on our response to convert the string data to bytes. The write method on the stream takes a slice of U8 and sends those bytes directly down the connection. They're talking about this line. Here's the response, converting it to bytes, which is a slice of like U8s, and then writing it directly to the connection. Because the write operation could fail, we use unwrap on any error result as before. Again, in a real application, you want to add error handling here. Finally, flush will wait and prevent the program from continuing until all of the bytes are written to the connection. TCP stream contains an internal buffer to minimize calls to the underlying operating system. And so they're just talking about here, we call flush on the stream just to make sure that before anything happens or returns, all of the bytes that were in said buffer, this one, or I guess in this buffer now, because the way they handle it internally, stream probably has its own buffer that it holds on to stuff and then just minimizes the number of write commands it forces the operating system to do. Minor optimization, yeah. Anyway, flush makes sure that the internal buffer for the stream is all written to. With these changes, let's run our code and make a request. We're no longer printing any data to the terminal, so we won't see any output other than the output from cargo. When you load localhost 7878 in a web browser, you should get a blank page instead of an error. You've just hand-coded an HTTP request and response. And that is true. We demonstrated that and saw it.